Okay, so let's start the class. I just want to bring your attention that the work done when gravity is doing work, okay, the equation is always mg and then the difference in height. So for example, when you are going down, gravity is doing positive work because it's going to help the system go faster. When it's going to go up, it's going to do negative work, right? Because it tries to slow it down. Now, for test number 3, remember, if you go back to the same place, the total work done by gravity will be equals to 0. It's not the case for friction, because friction is always doing negative work. Okay, so if you want to find the work done by friction, you will have to multiply the frictional force by the length of the path, right? So it won't be 0 because you're going to lose energy to heat with friction. But the work done by gravity is always mgh. So if you go back to the same height, no work is done. Okay, I wanted to emphasize that. So we talked about that when he's lifting the barbell, gravity is doing negative work, right? When he's lowering the barbell, gravity is doing positive work. So the net work will be 0. You're taking the can you sit in the corner? Only equation sheet, a scrap paper, and a pen. You can leave your stuff over there and take your calculator, scrap paper, and a pen. You can put your best. Okay, slide 30. Did we do this one? Yeah. Okay, so remember one thing I want to bring your attention to one equation is that the network, okay, equals to the change in kinetic energy. So that will be the kinetic work theorem. So the net work done on a system, okay? So the net work, so that means the sum of all the work will be equals to the change in kinetic energy. And when you're going to write the change in kinetic energy, so then you will have to write 0.5, the mass, and then you will have the final speed squared minus the initial speed squared. Okay? Now, if the network equals 0, so that means, is there a change in kinetic energy? Are you going faster or slower? No. Right? So that means there is no change in kinetic energy, which is the case if the net force equals 0. And we already know that because you remember the net force equals ma. A is the acceleration. So if the net force equals 0, that means there is no acceleration. You don't go slower, you don't go faster. So that's why there is no change in kinetic energy. Okay, which means there is no change in kinetic energy and the acceleration equals 0. Okay, so how do we compute the net work on a system? We can say it's the sum of all the individual work done by all the forces. Okay, that's one way. Or we can say this is equals to the net force times the displacement, and the net force has to be parallel to the displacement. So we're going to see problems where we're going to use the two ways to do it. Okay, so let's do slide 31. So you have a box and there is a 100 Newton force applied to that box, and the box moves 3 meters. Okay, so there is a box here. Okay, you are pushing here. Okay, and the box is going to move by a displacement here equals 3 meters. So you try to make the box go faster. Okay, so there is a force. The force is parallel and it's 100 Newton. So what's going to be the work done by you on the box? So that's going to be easy. Work is force times displacement. So that's going to be 300 joules. Agree? Mm-hmm. Now imagine that you have friction. So you are putting energy into the box, but now imagine that you also have some kinetic friction, and imagine that the kinetic friction is 100 Newton to the left. So it's stealing away energy, okay? It's removing energy from the box. So what's going to be the work done by friction on the box? It's going to be negative 300 joule. Do you all agree? Yeah. Force times distance. So we can say, okay, if I want to find the net work, I'm going to add all the works. So the work done by the applied force and the work done by friction. So the net work will be 300 minus 300, which is 0. So the change in kinetic energy equals 0. Or I can use a different way. Okay, I can say the net work equals the net force times the displacement. And it has to be parallel to the displacement. So what is the net force? To the right is 100, to the left is 100. So right minus left equals 0. So the net force equals 0 times 3. Okay, that's going to be also 0. So you have two ways to find the net work, right? So at the end, you find the balance of your account, how much was withdrawn, how much was added. Okay, you add them up. That will be the net work. Or you can find the net force, you multiply by displacement or the distance covered, and then you can have the net work as well. Okay? So that's not how. Okay, so let's see what do. Okay, let's do number 1. Try number 1. You can help each other, talk to each other. And I have chocolate today. You can look in the bag. I'm a little bit past the mid-semester, but it's fine. Okay, number 1 is easy, it's just algebra. So remember, kinetic energy equals 1/2 the mass and the speed squared. And remember, V is a speed, okay? So it's going to be a scalar. Okay, so how much jet ski had the same amount of kinetic energy? How much did you find? 86.4? Okay, let's try. So 1/2. So that will be the kinetic energy of the first one times 2.4 squared equals to, no? So that will be kinetic energy of the small one. So 1/2 100, and then v squared, and you are solving for v. So this one has a smaller mass, so we want to make sure it's going to move faster, but not that faster because it has a square. So first of all, you can cross out half, and then you can cross out, you go bye-bye, and then it goes bye-bye. So v squared equals 36 times 2.4 squared, and you take the square root. Oh, and you take the square root, right? You forgot to take the square root. 14.4. 36 times 2.4 squared, and then you take the square root. 14.4. Did you all do that? Right? Because you have to take the square root. So this is a relaxing problem. It's easy. It's very simple algebra. So much easier than kinematics. Okay, number 7. Think about it. Also easy. So they want you to find kinetic energy, which is 1/2 mv squared. And again, the v is the speed. So you are given the mass. How can you find the speed? Very good. Okay, it's meter per second. So you divide 5 by 4. And then you plug in it. 7.
1.25.
Yeah, you're right. Square. 5.47. Okay, 5.5. All agree?
Yeah.
And don't forget the unit. Okay, it's gonna be joules. Joules, it's like, it means Newton meters. Okay, because it's work. To get work, you multiply your force by a distance. So it's energy. The unit for work is joule. Work is energy in transfer. Okay, did I say number 3? Okay, so number 3. So these are easy problems, and in Dropbox, I think I go over them as well. So number 3. And you need to open your book, right? The textbook. It's meant to be open. So by definition, the net work done on the system. So here we have a wagon. Because there is a net work done, so energy is being transferred, then you're going to have a change in kinetic energy. So that energy goes into energy of motion. So when they say how much work, you need to use that principle, and then you can find the change in kinetic energy, which is 0.5, the mass times the final speed. I have no idea why I hide all the way up when I have so much space. 398. Everyone check this out. So you can do 3. You always you start with the inside and then you go out. So you go 3.3 square minus 0.8 square, enter, times 77.7, enter times 0.5. Especially for those who are late, I have chocolate here. Did you all get that? Okay. Joules. Okay. Another one that is easy. See, physics is getting easier. Okay, so how much work? Okay, that's also an easy one. Okay, so the net work done on the boat, so that could be the ng minus resistance from the water, so friction from the water, equals the change in kinetic energy, right? So it's going to be 0.5, the mass, times the final speed, final. So 0.55 square minus rest. So we have to put a 0 here. So you go from inside out, so 0.55 square, enter, times 879,000, enter, times 0.5, enter, and I screw up, so I don't know. So what you get? 265,897.5. You get a big number.
101.
Right?
Yeah, 132,948.
Joules.
0.700.
Okay? So usually you want to write that in kilojoules, so it's going to be about 133 kilojoules. So it's really not okay. So number 5, you are just using the equation for potential energy. Let's see, potential energy equals 0 here. And then the height is 33.4. .64 kilogram, and you have gravity pulling it down. Okay, so you multiply by 10 also. Okay, so that will be, you can say the work done by gravity. Okay, you can do that on the stone equals the force. So the force due to gravity is going to be 76.4 because that's going to be mg times the displacement. Okay, so that will be 33.4. So that will be your displacement or delta y if you want. That's one way to see that. Okay. So that's going to be okay, so you're right. So 2552 joules. Is that right?
Yeah.
Or you can say here it has some potential energy because that potential energy has the potential to be released when gravity is doing work on it. So we can say that the gravitational potential energy is always equals to m and g and the height above that level here. So it's a different way to look at it. So we can say it has potential energy. It's like store energy, and then that energy can be released. Okay, and that will be also 2552 joules. And before it's gonna hit the ground, all that energy is gonna be turned into kinetic energy, right? So here there is no speed, and here it's gonna move really fast before it's gonna hit the ground. So let's find the velocity, the final velocity. Find the final velocity before it hits the ground. Let's find. So it's going to speed up. We already did things like this for kinematics. So find the final velocity before it hits the ground. So we can say all that work done by gravity on the stone is going to turn into kinetic energy. Okay? And so kinetic energy, so it will be 0.5, the mass. Final speed is, I don't know. That's what I'm trying to find out. Okay, so sorry. So final speed minus 0. Okay, so all that potential energy is going to turn into kinetic energy. That's what we're going to do next. It is called conservation of energy. Or it's the same thing. You can say all the work done by gravity is positive, so it's going to make it go faster. It's going to increase the speed. So I can use that kinetic work theorem. Okay, so we have 2552 equals 0.5. The mass is 7.64. Final speed squared. Okay, you can do 2552 enter, divide by 0.5, enter, divide by 7.64, enter, and then you take the square root, right? So 2552, you divide by 0.5, enter, you divide by 7.64, enter, and then you take the square root, and you call back here, answer, to about 26. Did you find that? 26. Okay, so the final speed is 26 meters per second. And then when it's going to hit the ground, it's going to go into the ground, and then it's going to apply a huge force. So the ground will apply another force back, right? For every action, you have an equal reaction. And that's what kills. It's not the fall that kills, it's the landing. Because all that kinetic energy is going to go into destruction. Okay? Because you need a huge force to stop it. Remember, the acceleration will be up. So you need a huge force. What is that force here? When you hit the ground is pushing back on you, the normal force. Excellent. So the normal force, and then you have some weight, but you see that force here will be huge. That's what's gonna destroy. Oh, by the way, we already did that in kinematics, but in kinematics, remember we use that equation final speed square equals initial speed square plus 2 times the acceleration was minus g because it's falling, and here you have y. Very good, very good. And it's the same. It's going to be the same thing. You get exactly the same thing, right? If I multiply by 0.5 on both everywhere, so I go 0.5. I multiply by the mass everywhere. I'm gonna have 0.5 the mass plus 0.5 times 2 is 1, so I have m minus g and y, and we get the same thing, except y should be negative, so I should put a plus here. Okay, and then I get the same thing. So that equation in kinematics actually comes from the conservation of energy, or the work-kinetic theorem. Okay, so here maybe we're not going to do the math, although it could be a good exercise, but at least lay out the equation that you're going to use. And that slide comes from your book, Johnson and Kirknell, which I highly recommend, especially if you want to take the MCAT or go to physical therapy school, which is a good job because all those people working on the computer, it's not going to end well for the lower back. So now you have a spacecraft, and the applied force comes from the engine. Okay, it's pushing forward. The force stays the same, and you see there is an acceleration, right? So net force equals mass times acceleration. So for now, they want you to use the network, okay, applied to the spaceship equals the change in kinetic energy. So because there is a force applied over a distance, then there is a change in kinetic energy. It's going to move slower or it's going to move faster. But it has to move. If there is no distance, if it doesn't move, there is no work done. So lay out the equation, even if we don't do it all the way through, just lay out the equation. Okay, so the force, and the force has to be parallel to the displacement. The displacement is called S. I'm going to put S equals the change in kinetic energy. So the force is parallel, so I don't have to worry about cosine or sine. And the force is given, so it's going to be 0.056. Okay. I should put delta x because we usually work with delta x, so let's put delta x. So do it, because more you do now, less you have to do at home, isn't it? So delta x is the displacement, which is 2.42 times 10 to the 9 equals to the change in kinetic energy, so that will be 0.5. And what's the mass? 474. The final, that's what you want to find, minus initial. Isn't it? Okay. So when you have to do something like this, you start from here, right? So you go, if you want, you can do it with me, or you can do it on your own, okay? Times that thing here, So 2.42 times 10, so power of 10, that will be second, comma, 9. Okay, enter. This one on the other side, so you divide by 0.5, enter. This one on the other side, so divide by 474, enter. And then you want to isolate this one, so you need to add on both sides, so plus 275 square, enter. We good, and then we have to take the square root. 805? 805, very good. 805, do you all agree? You see, you can do it with your TI. So that way we review algebra, doesn't hurt. Okay, so very relaxed today. Nothing too hard. Okay, slide. Let's see which one we're gonna do. Let's try by number 4. Let's try number 4. So there is a force applied, but you see the force has two components. One component is perpendicular to the displacement, so we don't want this one. It doesn't help making it go faster. We only want the component parallel to the displacement because that's the only one that make it go faster, right? That provides the acceleration. So don't do it. Okay, so this force here has a magnitude of 100 Newton, and the angle here is 60 degrees. So this one, it's not the only force applied. You might have friction, for example. You're gonna have the weight, and you have the normal force. It has a X component, and it has a Y component. And so that will be the displacement delta X, 10 meters. So we can review also for the final, right? Let's review. You also have the normal force here pushing up. Then have the weight. You see, whatever is up has to be equals to whatever is down. So let's do review, right? The weight will be equals to the normal force plus the Y component. And maybe you're gonna have kinetic friction. Okay, let's go back to the question. So the work done by this force here, right? So the work done by the applied force on the wagon. So how much energy is being transferred? So you transfer energy from the person to the wagon. So which component I'm gonna use? Do I use 100? Do I use F sub X or F sub Y? Which component is making it go faster?
No, X.
X. The Y component is lifting it up. Okay, it's good to lift up because it decreases friction, but it doesn't help. If a component is perpendicular to the displacement, no work is done. It doesn't help. So I'm only using the X component. You see, it has to be consistent. If you have a delta X here, you need the X there. X, delta X. Agree? So the component here will be 100. Cosine or sine? Cosine, very good. And displacement is 10, you're right. So cosine 60 is half, so yes, 50. So 50 times 10 is 500 joules. Agree? Okay. And now they ask you, okay, now if you have friction, what will be the work done by friction on the wagon? So it means friction is taking away energy, right? It's losing energy. That energy goes into heat. Maybe it's noise. Noise is a form of energy. So is the work positive or negative? Negative, very good, because it's taking energy away. It's trying to make it go slower. So that will be the force, which is 40 times the displacement, which is 10. So that will be negative 400 joules. Do you all agree?
Yeah.
This is here. That will be the frictional force and delta X. So frictional force, I don't worry about component. There is no component because it's always along the path. So always along the path, right? Always. So for example, in that case, if I want to show you, okay, I can do that. Here, on its way down, the frictional force will be this way, right? It's along the path. Do you agree? Always along the path because it's rubbing against each other. And remember, you're going to have the normal force here from the surface to the system. The weight is straight down. And we have some kind of inclined plane. And remember, the component of the weight down to the slope is what? mg sine. And the one perpendicular is mg cosine. Don't forget, okay? So anyway, so now I need to find the net work. Yes, so one way to do it is just to add each individual work. So 500 minus 400 will be 100, which is equals to the change in kinetic energy. Okay, see, easy. Do you all agree? Or a different way to do it, you can say the net work equals the net force parallel to the displacement times the displacement. And what's going to be the net force? It will be 100 cosine 60 minus 40 times 100, and you will get the same thing. Not times 100 times 10. And if you do that, you will find 50 minus 40 is 10, so you will still get 100 joules. So it's the different way to do it. You can find the net force along the x multiplied by the displacement. But you have to find the component. You have to find the right component. Okay? Mm-hmm. And then what did I plan? I plan to do number 3. So do it on your own. Do it. So first, you want to draw. You have to draw and have a free body diagram. So 410. So you see you have a big force up. I'm going to put the magnitude here. It's a vector. The weight pulling down. So already you can see that there is a net force up. So of course it's going to accelerate up. And then it's moving. Displacement delta y equals 2 meters. And to make my life easier, I'm going to say up is plus and down is minus. Okay, so the work done by the pull on the stone is going to be equals to what? Okay, it depends which way you do it. So you can do it like the net force. We can do 410 minus 42. And then you multiply by the displacement, which is 2. Yeah, you can do that. Okay, so maybe it's easier to do that, so you can do 410. Anyway, you already know that the work has to be positive because there was a winner up, so it's going to accelerate. So instead of doing this way, you can say, okay, the net force is 410 minus 32. Okay, you can do that, which is 378 Newton. So the net work will be equals to the net force times your delta y, which is 378 times 2. Right, joules. So that's one way to do it. Maybe the easiest way. Otherwise, you have to break it down. You have to say the work done by the pull, pulling here will be 410 times 2, okay, which is 820 joule. Is that right? The work done by gravity, it's going to be a negative work because it's trying to decelerate, so minus times 2, so it's minus 64 joule. So the net work will be, and you should get 756 joule. Right? So you can do it 2 ways. Okay, and then there is a question. Next question is just like to review. If the stone is 5 meters above the ground, what is its potential energy? So potential energy is by definition mgh relative to the ground. Okay, so that's going to be what? Or mg, that's the weight, so it will be 32 times 5. Okay? Okay, so that's easy. And then the tree. Okay, let's do the tree. But you need to, first of all, you have to draw the situation. Okay, so you want to draw the situation. Let's see, you have a truck. I don't know why it's a truck, because it says a car. Well, I don't know. It's a car. That's how I draw car. it has a speed of 12 meters per second, and it has a mass of 2,000 kilograms. And then you have a tree minding his own business here, happily living his life of tree. And then it's gonna collide. And it comes to a stop. So the tree doesn't move, but you see that the car, it's a giant tree, I guess. See, the car went into the tree. So that's about the idea. That's the idea about energy. If there is energy, then you can go into something, which means you can apply a force over a distance. Okay? So in that case, you see, you went, or the car went into the tree by a distance of 50 centimeters. So smaller is the distance, very bad it gets. So of course, if you're gonna, all that energy, kinetic energy is gonna go into applying a force over a distance, but for every action, there is an opposite and equal reaction. So if you apply a force on the tree is gonna apply a force on you, and it will be the same. Okay. So let's try to answer the first question. Find the change in kinetic energy. Right? Negative 144,000. So change in kinetic energy will be 0.5, the mass. So larger means worse, and then faster even worse. So final speed square minus 12 square. So the change in kinetic energy will be negative because you are losing energy. Okay? So 12 square is 144. Half of 2,000 is 1,000. So negative 144,000 joules. So all that energy is lost. Where did it go? Right, to destroy, right, to destruction. So all that energy goes into applying a force over a distance, and the same force will be applied back. So smaller the distance, larger is the force. So that's why if you crash into something, airbag will help because it will increase the distance you go into the airbag. If you crash on the windshield, the distance will be so small, the force will be huge. And that will be bad. So for every action, you have a reaction, or for every action, you have a reaction. Find the size of the force. Okay, so the work done by the tree on the car will be equals to the change in kinetic energy. So all that kinetic energy is going to be lost. And by definition, if there is a change in kinetic energy, that means a force was applied over a distance. Is that clear? So how come it lost that energy? Because there is a force from the tree on the car over a distance. And here we suppose the distance is parallel. Okay, so we have minus 144,000 equals the force on from the tree to the car, and the displacement is 0.5. Negative half 72,000. Joules. No. Newton. So check. No. No. You divide by 0.5. So you multiply by 2, right? So what you get? You multiply by 2. When you divide by 0.5, it's like you multiply by 2. Okay, yeah. So it's going to be 288,000 Newton. Do you all agree? Mm-hmm. Okay. So that's the force from the tree to the car. So then the force, that's what they want. Okay. And the car to the tree will be the same force. And this is bad. If you want to know in pound, you divide by 5. So that's quite large. Yeah. So it's not good. Okay, so which one we want to do? So here, so when you have a spring, when you have let's say you are doing Pilates, right? So you have those bands, you can stretch out, right? You can stretch your band. So when you are doing this, you are stretching out your band, you are doing work on it, you are applying a force over a distance, and if you let go, it's going to go into kinetic energy, right? Mm-hmm. And there is a simple equation that says, so let's say you have a spring here and it's not being stretched. Maybe you're going to have a mass here, so it's happy here. When you're going to stretch out your spring, I think we already do something like this, right? So you stretch it out, so you're doing work on it. Okay, so you're holding this, you're holding it, so you are storing energy into that spring. That energy is called elastic potential energy. Okay, because you did work on that spring. And if you let go, all that energy is going to be released into kinetic energy. So it's another kind of potential energy. And we can show that if the spring is stretched by an amount of X, that elastic potential energy will be equals to 1/2. And then you have K. So a K is a constant and it depends on the kind of spring you have. It depends on the material, X squared. So this is called the spring constant. It's Newton per meters, and that will be in meters. So it's just an equation. The elastic potential energy depends on how much you are stretching out the spring or how much you are squeezing the spring. Just an idea, like if you go to the gym, here is an easy demo you take those sometimes they have at the gym, they have those band, the elastic, the Pilates band. Okay, and you take like a very light weight, like maybe 1 pound, and you measure for 1 pound. You can measure by how much it has been stretched from its initial position. Okay, so no, I'm rewinding. Okay, so that will be your unstretched Pilates band. Okay, and now you put 1 pound. So that will be the stretch X. Now, if you put 2 pounds, you should be able that you have now, the stretch will be twice as much. And if you put 3 pounds, it's going to be 3 times more stretched. That's just an idea that just came up in my head. So you can do it at the gym if you want. So anyway, the force here, but we don't worry about it. But like if you are curious, the spring force here will be Kx. That will be the restoring force. So anyway, that's the equation. I'm just asking you to use the equation for number 7. Number 7. I think we did it already in the previous unit. Did we see Hooke's law Kx? No, we didn't. So anyway, potential energy, so how much energy is stored inside the spring will be equals to 1/2 kx squared. Which is 1/2, you just plug it in. 150 times 0.3 squared. Right, so 0.5 times 150 times 0.3 squared. Okay? Let's see. It's called Hooke's law. So you have a spring, so that could be a Pilates band, and it's not being stretched, so it doesn't have energy stored inside. Now, if you stretch it, like if you pull it down, so I'm going to pull it down like this. Now you have energy being stored inside. And if I want to find how much energy is being stored, you're going to do 1/2. Then you have a spring constant that is given to you times the stretched square. So 1/2 kx squared. Okay? It's just an equation. Don't have to worry about it. But it's just to give you an idea of what it means. Maybe we'll get back to that. It was a tangent. Don't worry. We'll get back to it. Okay, so now we move to conservation of energy. So conservation of energy is just a different way to write that kinetic work theorem. The net work equals to the change in kinetic energy. So it's just a different way to write exactly the same thing. Okay, so we can say that's one of the fundamental law of conservation. You have conservation of mass, you have the conservation of electric charge, you have conservation of spin, you have conservation of momentum, and here you have conservation of energy. So if there is no friction, if there is no air resistance, the total amount of energy before equals the total amount of energy after, which means potential energy plus kinetic energy before equals potential energy plus kinetic energy after. So I'm going to show you what I mean by that. Here, for example, here, what kind of energy does it have relative to ground level? Potential. So you see, it has 600,000 joule of potential energy. It has no kinetic energy because it doesn't move. So the total amount of energy, which is called the mechanical energy, will be 600,000. Do you agree? Mm-hmm. And then it's going to start moving. Okay, so it's going to speed up. So it's losing what? Potential or kinetic? Potential energy, very good. And it's going to gain kinetic, very good. So if it has 200 kinetic, it needs to have 400 potential to make sure that the total amount of energy stays the same. So it's like when you buy Bitcoin and dollars, for example, or if you mine Bitcoin, you're going to have that amount of Bitcoin, that amount of dollars. Let's say you cash in your Bitcoin, the total amount will be the same, except you're going to have only dollars instead of Bitcoin and dollars, right? Mm-hmm. And then it goes down. Here you have more kinetic energy, less potential energy. But when you're going to add them up, you're going to get to the same amount. Does it make sense? Okay, at the end, what type of energy we're going to get? Kinetic. So how can we write this equation? Very simple. And it's all scalar. You will appreciate the fact that there is no vectors involved. You're going to say before equals after. So before we have gravitational potential energy plus maybe sometimes we have kinetic energy. After, maybe we have gravitational potential energy. I'm going to put a prime plus kinetic energy prime. So in that case, before, did we have any kinetic energy? No. So in that case, that was 0 and that will be 0. But the total amount of energy will stay the same. It's just switching back and forth between gravitational potential energy, kinetic energy, gravitational energy, potential energy. Okay, so for example here, it has kinetic energy. Do you agree? Mm-hmm. So at the top, it does not have any kinetic energy. So what should the potential energy be? 50 joules. 50 joules, very good. Right? And here, what will be the kinetic energy? 25, because the total amount has to stay the same. Here could be for test 3, something like this. Here, remember, kinetic energy goes with the speed square. Very good. So from 30 to 60, you multiply the speed by 2. So the kinetic energy will be multiplied by 4. So if you have 1 million here, you're going to have 4 million there. That's why you don't want to drive too fast. It's a killer. Kinetic energy is a killer. From 30 to 90, you multiply by 3. So kinetic energy is multiplied by, very good. So here you have 9 million joules. Okay, let's think about this one. Remember, the potential energy only depends on the height above the ground. So if you have potential energy here, which is 30 joules, here it's going to be 30 joules because it only depends on the height. It doesn't matter if you are up an inclined plane or a pole or a staircase. So here it will be 30 joules. If it's gonna fall, right, free fall, at the end, it's gonna be kinetic energy will be 30. Very good. Okay, so all the potential goes into kinetic. And you see you have steps. So what will be your potential energy here? If it's 10 here, it's going to be, you have 3 steps. Huh? 10 joule. So here it's going to be 20, and here it's going to be 30. Okay, so it's not that hard. So this is a very old picture, okay? This is 20 years old. Of course, I didn't change much, right? So potential energy 15,000 joule. And then, so if potential energy is 12 to 50, kinetic energy will be exactly to add up to 15,000 and 7,500. So kinetic energy will be 7,500. Very good. And same thing here. It will be 11 to 50, 0, and here it will be 50,000, right? That's the same picture I put on canvas. It's okay. So 100 joules, okay, you get it, right? So at the potential energy will be 100, and here it will be 25, and here it will be, okay, you see how easy it is? So this is a typical demo with a pendulum. So here, if it's not moving, what kind of energy does it have here? Above the bound? Potential. And the potential will be the weight times the height. Do you agree? And all that potential is going to turn into kinetic. And kinetic will turn into, and it will be perpetual. If there is no resistance, you swing back and forth between kinetic and potential. So it's also a very famous demo, but the professor who does it the best, who is very famous to have done this experiment, is a professor named Walter Levin. So he used to teach at MIT, and he will do those demos, amazing demos. So he will take like all day to prepare his demo. So very famous. So I'm going to share that with you.
Now I want to return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10 is about 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, they're called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish the building. You just let it hit, and it breaks the building. And that's the whole idea of wrecking. So you're using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust.
Okay, so why is it so dangerous? Because if you don't let go, and by accident you give it like a little momentum, a little push, then it will add up, right? It will have potential plus energy from your push. So it will go higher on the other side, and when it comes back to you, it will go higher and it will crush your chin. Also, if you duck, like if you move forward, that's it, you're dead. I'm not dead, but you are good for the ER.
The conservation of mechanical energy
Right,
for
plastic
100%.
surgery.
I may not trust myself. I'm going to release this object, and I hope I will be able to do it at zero speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it zero speed, then this will be my last lecture. I will close my eyes, I don't want to see this. So please be very quiet. I almost didn't sleep. 3, 2, 1, 0.
Imagine if you start to be scared, that's it. So it can go bad. So that's a video I found a long time ago on YouTube, and then it was removed.
Do ciężki 15 kg.
What?
Did it go well or no?
No. Okay, you might close your eyes.
No.
Okay, if you are very sensitive, you can close your eyes.
No my też się boimy.
It's a old boat. She moved forward. And that's bad decision.
Yeah.
If that happens in the US, oi, boy, you will get like a lawsuit, like
Driving a
she. Yes, she dug forward. You're not supposed to move.
It's better maybe to do it up against the wall.
Like, go against the wall, and when you let go, you have to let go.
Yeah.
Yeah, she didn't have a very good point of reference, I guess.
And then it was removed, but you know, I had time to download
It
it.
wasn't bad.
It wasn't bad.
No, she's not going to be. I mean, she's just gonna break a few teeth, maybe a teeth.
It's gonna chill weird for a while.
So scary. Dude, I was like, it's at your own, I would tell us, it's at your own peril. You move.
Okay, so let's try. That's a real story. So it used to be a thing in Niagara Falls. I don't know if you read about it, like in the early 20th century. People will People will do it for money. They will go on top of the falls, get inside like a tunnel, not a tunnel,
A keg or barrel.
a barrel,
Yeah.
a barrel inside. There was an old woman who did it with her dog, and fall down the fall, right? For money, or for the challenge. And in 2003, he did that, and I not inside the barrel, just did that. He got fined, but you know it's Canada, so it's only $3,000. Yeah, but on the US side, I don't know how much he would have been fined. So you can find the speed. Okay, so what you want to do is potential energy before equals kinetic energy after. So I don't know if he was maybe he was Canadian. Niagara Falls, it's a great place to visit. Okay, it's very nice to visit. So the kids, when they are in college, they go to the Canadian side because they can drink. So 50 meters here. So you can decide that here your potential energy equals 0. So he will be in free fall. So here he has some final speed. Initial speed equals 0 here. So before equals after. So potential energy before plus kinetic energy before equals potential energy after plus kinetic energy after. So before there is no kinetic energy, and after there is no potential energy. If you say that that's the water, if you say that potential energy equals 0, so you have mgh equals kinetic energy, so that's going to be 0.5 mv squared. And we did that in kinematics, right? It's when something is falling in free fall, so there is no air resistance, you can use kinematics. You see the mass cancel out, because in free fall the mass does not matter, and you get this nice answer. So it will be the square root of, okay, because you have gh equals 1/2 v squared. You multiply by 2 on both sides. Okay? So you have the square root 2 times 10 times, what's the height? 50. 32, which is like 60 miles per hour. It's good that you have water. You know, if he falls on the water with, yeah, that, yeah, right? That has to be the head first, because otherwise, ouch. So, unlawful.
Doing a star or just spectrums?
I don't know, for maybe 2003, did we have YouTube 2003? No? No?
Yeah, it was in 2000.
So I don't know, just for the buzz, maybe. Okay. I just want to show you how I close all the window, right?
It was the female you. Or those that came. How do you know? Then probably came.
He knows everything, I don't know. Okay, so what do you think of this situation? So you have potential energy. Okay, then before she hits the trampoline, what kind of energy is going to be? Kinetic. And then she hits the trampoline, and the trampoline is going to stretch out. Elastic potential energy. That elastic potential energy goes back to kinetic. That will go back to potential. So potential, kinetic, elastic, kinetic, potential.
She's probably Jim.
Looks very hard. So here another idea for a demo. Potential, kinetic, and I want to show you something.
Probably land on my head.
So this is
much and you're hitting the wall.
So he's an artist, and the idea is that in life, even if we fail, we should keep trying. We should keep trying, never give up, right? Failing is part of success. So it's a positive note. So this is potential, kinetic, elastic, kinetic, potential. And if you cannot sleep at night, the music is great. Potential, kinetic, elastic.
If I just fall asleep and have an anxiety, some long It's having so much fun. Your badges.
Wow. It's very impressive, huh? So what he's doing here is using his muscles to pump it up, right? He's doing work with his muscles to increase the energy level so he can get back to the initial height. That's very athletic. So what I mean by that is sometimes like, so I don't know if you do skateboarding. Is it called skateboarding? Skateboard, right?
Yeah.
So you have a half pipe all over they have that. And the idea is that you have kinetic. If you don't do anything, you're going to go to potential, but you're not going to be going very high. So what you're doing is you pump. So it means you squat and then you extend. So that way you are doing work with your muscles. So you put in some additional energy. So you have kinetic energy plus the work that you are doing will be equals to the potential energy. So here's another idea. If you like skateboarding, you can show that if you pump, you're doing work, so you put more energy into the system. Kinetic plus the work done by you equals potential. It's called pumping, I think. I don't know how to, I never was able to do skateboarding. It didn't exist at my time, but they have those things that you put under your feet, like those special shoes, right, with the wheel.